We begin this class from chapter 6 of the text. It's a little bit unfortunate that I have to do this first recording in the night. But anyway, that's okay. So we'll be talking about inverse function in chapter 6. And to do that, it would be very fine if we could review what functions are. I believe many of you may have come across functions in pre-calc or calc 1. But this place, we just consider a little bit about functions. We are not really going in deep very much into functions. So as you may have already known, a function could be defined as a rule that assigns to each element in a set D exactly one element called f of x in another set E. Usually, the set D and E, as far as this class is concerned, would be subsets or sets of real numbers. The set D is usually called the domain of the function, while E is called the range. F of x is the value of the function f at x. We usually read this as f at x or f of x, as I said earlier. The range of f is the set of all possible values of f throughout the domain. So if I want to define this maybe a little bit graphically, we could say we have a set D, and another set E. Now, I could say, fine, my set D has elements maybe A, B, C, like that going. Could be 1, 2, 3, could be anything. And my set E has elements maybe 1 and 2, and maybe other elements. So a function would be a rule that assigns to each element in D exactly one element in E and not more than one. What do we mean by not more than one? If A is assigned to both 1 here, and maybe A is also assigned to 2, then this wouldn't define a function. It's actually a map, but it's not a function. So for it to be a function, it must be every element in the domain must have only one image. So we could assign this to D, and C could also be assigned to 2, like that going. So the rule of this assignment is what we call F. Now, the symbol that represents an arbitrary number in this set D is called an independent variable, while the symbol that represents any number in the range in this set E is called a dependent variable. Why? Because for each element in this domain, we can determine what is mapped to by F. Sometimes it would be nice for you to think about functions like machines. And if you have a machine, it does something. So if you put something, maybe an input into a machine, it transforms it into whatever according to the rule of that machine to give you an output. For instance, you think about a blender. If you put things in a blender, you expect it to come out blended. You don't expect it to come out cooked. You don't put maybe a tomato into a blender and expect to get a rice. No. So it does something, and that thing it does is actually the rule, is what we see as the function. That's why we say here that the outputs depend on the rule of F. Now, moving forward, we can define what a one-to-one function is. A function is said to be one-to-one if it never takes the same values more than once. What do we mean? Well, if we have x1 and x2 in the domain of the function, then if x1 is not equal to x2, if the function is one-to-one, f of x1 can never be equal to f of x2. Another way to think about the function, maybe if it's defined graphically, it is one-to-one if no horizontal line passes the function more than once. Now look at this diagram here. Let's say this blue line defines our function f, y equal to f. Now for this blue line, you could ask yourself, if we choose x1 here and x2, we want to ask ourselves, x1 and x2 are not the same, but do they actually have the same value for f? Is f of x1 equal to f of x2? If that is the case, then this function f is not one-to-one. But if f of x1 is not equal to f of x2, then it's one-to-one. So clearly, the function shown by this graph here is actually not one-to-one. Let's try to use some examples to understand this concept a little bit more better. Consider a function f of x equal to x squared. And here we are talking about the domain should be all the real numbers. Is this function, if we take the domain to be the set of all real numbers that we denote as R, is this function here one-to-one? Well, you could ask yourself, in the set of real numbers, I know that my 1 is not equal to -1. However, f of 1 is equal to 1 squared, which is 1. F of -1 is equal to -1 all squared, which is 1. That tells me that my f of 1 is equal to f of -1. However, my 1 is not equal to -1. So the function defined by f as x squared is not one-to-one. Similarly, you could show that this function here, g of x, x squared minus 2, is not one-to-one using the same property. Another way we could do this, like, what if we don't know, maybe we can't choose a particular number? Well, we could say, basically, if we choose any element, maybe x1 and which is not equal to x2, we want to see whether g of x1 is it the same thing as g of x2. Generally, this may not work because x1 and x2 are not defined. Probably if both of them are positive, then what we can't quite verify. So it's better to, maybe if you want to show that a function is one-to-one, you could use the procedure saying that if I pick any two things, I can show that the function or the value of those two things when applied to the function are not the same. But if we want to show that they are not one-to-one, we could just like give one example or pick a value which makes them not to be one-to-one. In this case, if we still pick like 1 and -1, we'll say that g of 1, which is going to be -1, is still equal to g of -1. This tells me that since my 1 is not -1, but g of 1 equal to g of -1, this function, g of x, defined as x squared minus 2, is not one-to-one. It's not one-to-one. Actually, this is a shorthand form of writing one-to-one. Now, let's maybe think about a function defined like this. Well, the exponential function goes this way. This doesn't really look good, but yeah. Let's assume this is a f of x. Is this function one-to-one or not? Well, you could ask yourself, is it possible for me to draw any horizontal line and it will cut this function twice or cross this function twice? Well, any horizontal line you draw can only cross this function only once. So by the horizontal line test, this function is one-to-one. However, if I have maybe a function, probably, yeah. So we've considered f of x equal to x squared. Graphically, the function x squared looks like a parabola this way. So this is the same thing as f of x equal to x squared. By horizontal line test, you could show that any horizontal line you draw above the origin actually crosses this line or this graph more than once. So that tells me that this is not one-to-one. So if probably you understand the graph of a function, you could use it to show that a function is one-to-one or not. But if not, you have to follow this other procedure. And finally, we have the last example here. Now we have cosine, the cosine function. If we add 1 to this, graphically, if you draw this, you may get what it is. But if we don't want to do it graphically, can we show whether this function is one-to-one or not? Well, if you know the graph of cosine function, it looks like this, like something like this. This is how the graph goes. So we know that this graph cannot pass the horizontal line test, because if you draw any horizontal line, it's going to cut this function many places. However, how can we show that the function is not one-to-one? Well, I know my cosine function is periodic. That means every 2 pi, the value repeats itself. For instance, cosine of 0 is equal to 1, and this is still equal to cosine of 2 pi. So I can show that 0 is not equal to 2 pi. However, my h of 0 is equal to 1 plus cosine of 0, which is going to give me 1 plus 1, and this will be 2. This value will be the same thing as 1 plus cosine of 2 pi, which is basically h of 2 pi. So we have that 0 is not equal to 2 pi, but h of 0 is equal to h of 2 pi. Therefore, we conclude that h of x, so defined, is not one-to-one. A short way to write this is not one-to-one. This is not really 1 minus 1. Instead, it is one-to-one. Now, we've seen that a function could be one-to-one. We've seen that it's not. It could also not be one-to-one. So if a function is one-to-one, what else can we say about that function? It has more properties that we want to explore. Now, if a function is one-to-one and has domain A and range B, the inverse of that function, if we denote the function by f, the inverse will be denoted by f inverse. It has the domain B and range A, and is defined to be f of x equal to y if and only if, this should be double arrow here, if and only if f of x is equal to y. So this is the way we define the inverse of a function for any y in the range. Now, if maybe you want to think about this the way we did it before, imagine that we have the set A and the set B. This set here is A, has value maybe 1, 2, 3, is the domain, and the range has value 0, 1, 2 is the range. Since this function is one-to-one, each element in the domain maps to only one element in the range. Maps to only one element in the range. So here, the rule that assigns to each element in A another element in B is called f. The inverse of this function f is the rule that takes every element in this B back to its pre-image in A. So since this is one-to-one, I can actually find out where each element came from. So this rule is what we call f inverse. Now notice that f inverse goes from B to A. So B is the domain of the inverse function, while A is the range. So basically, if I have a function f with domain A, I have like f, and f has domain and range. The domain of f is A, and the range of f is B. If f is one-to-one, it has an inverse defined above, and the inverse of that has domain B and range A. We'll see how this works graphically later on as we go. Now, you have to know something at this point. F inverse is written this way. It's not the same thing as the reciprocal of f. Like, it's not the same thing as 1 over f, but it's read f inverse. So if I say something like f inverse of x, this is not the same thing as 1 over f of x. No. If I want to talk about 1 over f of x, then that would be f of x. I'll put this whole thing inside the bracket and put -1 here. This gives me the reciprocal. This is not equal to that, please. So this is what is 1 over f of x. So please note this concept. It's really very important. Note this. Moving forward, let's try to see how this works with some examples. Now imagine that you have a function that is defined for some values. They say f of 1 is 5, f of 3 is 7, and you are asked to find f inverse of 5 and f inverse of 7. Well, I know that since my f of 1 is equal to 5, f inverse of 5 should be equal to 1. Remember how we define f above, f inverse here. F inverse of y is equal to s if and only if f of x is y. So f inverse of 5 is equal to 1 since my f of 1 is equal to 5. Similarly, f inverse of 7 is going to be 3 since my f of 3 is equal to 7. The second example defines f as an integral, and now we are asked to find f inverse of 0. This looks a little bit weird. Like, how do we find f inverse of 0 when we don't even know what f is? However, if you notice from your calculus class that if you have a definite integral at a point a of any function f of x, this is going to be 0, no matter what the function is, as far as it's integrable. So from this definition, f of x is defined as the definite integral from 3 to x. I know that if I want this integral here to be 0, then I can evaluate it at 3. So I would see from observation that f of 3 would be the integral from 3 to 3 of square root of x squared plus 1 dx. And because I'm integrating at the same point, this is going to be 0. From Calc 1, you must have seen this. So here we've shown that my f of 3 is equal to 0. So my f inverse of 0 here now becomes 3. So sometimes it may be necessary for you to find out the inverse of a particular function at a point with other concepts you may have known somewhere. Finally, we want to consider cancellation equations before we move to the next part of this video. Now, by definition, we define f inverse of x to be equal to y if and only if this should be a double arrow. This should be a double arrow. If and only if. Actually, this arrow here means if and only if. And only if. It means whatever you have at the left hand side implies what is at the right, and whatever you have at the right implies what you have at the left. So f inverse of y, I'm going to write this here, there is a little error here. F inverse of y is equal to s if and only if f of x equal to y. We've seen this definition above. Now this implies that my f inverse of f of x is going to be this. Well, what do I mean? Why do I say that? Anyway, let's look at this. Now imagine if y is your f of x. So that tells me that my f inverse of y is going to be f inverse of f of x. By definition, this is x. For all x inside the domain, and the domain of f inverse here we can consider to be A. Or the domain of f is A because f takes value in x. F takes value in A, and anything that comes out of that is in y, is in B, which is the range, which is the domain of f inverse. Similarly, if I define my f inverse, if I let my f inverse of x maybe to be equal to y, this implies that my f of y is equal to x. So with that in mind, my f of f inverse of x basically would give me the same thing as f of y, which is x, from what we got here. So that's why we have this at this point. Now remember, f inverse takes value from B, which is the domain of the inverse function and the range of the function itself. Now, how does this cancellation equation works? Now, verify. Let's consider that we are given f of x is equal to x cubed. Well, basically, the graph of this function goes like this, comes like this, passes through the origin. It's not too good, but it goes this way. Now, this passes the horizontal line there, so the function is 1-to-1. That tells us that the inverse exists. And the inverse of this function, f inverse of x, is equal to x to the 1/3, or the cube root of x. Now let's try the cancellation equation here and see whether it works. What is my f inverse of f of x? Now this is the same thing as the f inverse of, what's my f of x? X cubed. So this is going to be f inverse of x cubed would be the same thing as x cubed all to the power of 1/3, which will be x 1/3 times 3 is going to be x. Similarly, f inverse of x is equal to f inverse of x is x to the 1/3, and this will be x to the 1/3 by definition of f to the power 3, and this will give me x. So this is how the cancellation equation works. We'll be seeing this cancellation equation very often as this class proceeds.